In this video we're going to look at the Excel function TDist. It handles the student t distribution, and the function operates in two modes. It operates in a one-tail mode and a two-tail mode. So in the one-tail mode, if you type TDist, open parenthesis, t, comma, the degrees of freedom, comma 1, the 1 stands for one tail, what this will do is return for you the area under the student t distribution to the right of the value t that you give it. So it's returning a right tail, single right tail in a student t distribution. In the two-tail mode, if you do TDist of a t value, comma, degrees of freedom, comma 2, it's going to return for you the area of both tails combined that are outside of t and negative t for the t value that you give it. You always have to give TDist a positive value. It will give you an error if you plug in a negative value there. So you have to learn how to use this thing to get the areas that you're really interested in by giving it the right t value. Let's take a look at an example. In this class we pretty much only use the TDist function to do hypothesis tests involving means. In this example I'll be looking for a hypothesis test for the difference between two independent means. The problem says, assume that the two samples are independent simple random samples selected from normally distributed populations. Do not assume that the population standard deviations are equal. Statistics from the ages of successful and unsuccessful applicants for a promotion are given below. Treat the data as samples from larger populations and use a significance level of 0.1 to test the claim that the unsuccessful applicants are from a population with a greater mean age than the mean age of the successful applicants. So as you can see, this is not a hypothesis test for a single mean. This is comparing two independent means. The assumptions that were laid out in the problem ensure that we can use the student t distribution to model the sampling distribution of the two means for this situation. That's why those are there. So in this area I have what I declared population 1. Those are the unsuccessful applicants. The sample size was 23. The sample mean was 49 years of age with a sample standard deviation of 7.2. The second population, those are the successful applicants. The sample that came from that population has sample size 30, sample mean of 47.5, those are years of age, and sample standard deviation of 5.2. We're testing the claim that the unsuccessful population has a larger mean than the successful population. So my alternate hypothesis is going to look something like mean 1 minus mean 2 is greater than 0. Another way to think about that is just population 1 is unsuccessful, population 2 is the successful. The difference, 1 minus 2, being positive just means that the first population has a higher mean age than the second population. That's precisely what the claim asked us in the question. So if that's my alternate hypothesis, my null hypothesis is going to be the boundary, which means mean 1 minus mean 2 is equal to 0. Now I need to compute standard error, and I need to use the standard error formula that corresponds to two independent samples. And that looks like square root of the first standard deviation squared divided by the first sample size plus the second standard deviation squared divided by the second sample size. And that sum takes place under the square root. This is called a standard error again because I don't know the population standard deviations, so I'm using the sample standard deviations to approximate those, and I call this number a standard error instead of a standard deviation. The degrees of freedom, the convention we'll be using in this class is we look at the sample size minus 1 for both samples and choose the smaller of the two. So our first sample has size 23, so 23 minus 1 is 22. The second one has size 30, 30 minus 1 is 29. The smaller of those two is 22. So for the purposes of carrying out this hypothesis test, we're going to use a degree of freedom of 22. In reality, or if you're using other statistical software, if you're letting Excel do this work for you in some kind of a package or an applet, it will use a more complicated formula to get a better degree of freedom estimate. But this is the convention we'll use here, unless the problem actually tells you what degree of freedom to use. Once I have that, I need to compute my test statistic. The t-test statistic is still just a z-score, so I'm computing it in the exact same way. I'm taking the observed sample differences, sample mean differences, so that's 49 minus 47.5, and if I'm being technical, I'm going to subtract from that the hypothesized difference of means, which is really 0. That's coming from my null hypothesis. Of course, I didn't really need to type minus 0, but I wanted to do that to emphasize that I'm taking the observed difference minus the hypothesized difference. And I'm going to divide it by the standard error we just computed. This is just a z-score. The t-value, or t-score, and z-score are really the same thing. The difference in this case, compared to what we do for proportions, is we don't use the normal model to compute a p-value. We use the student t model to compute a p-value, and that's what we'll need the TDist function for. In order to determine whether I'm in the one-tail scenario or the two-tail scenario, I have to look at the alternate hypothesis. The alternate hypothesis just says that this difference of means is positive, which means I'm only interested in the right tail. So this is a one-tailed situation. So all I'm going to do is take TDist, I'm going to feed it the t-value I just found, degrees of freedom that we just computed, which was 22, and it's a one-tail, so I only want to put 1 for the number of tails. What this will return for me is the area to the right of my t statistic under the student t distribution of 22 degrees of freedom. So it looks like I got a p-value of 0.2. 0.2 is huge, there's a 20%. That is not smaller than my 10% significance level. So the p-value is not small enough. P-value is not less than alpha, so we fail to reject our null hypothesis. In context, that means that we found that this sample does not provide significant evidence that the unsuccessful population has a mean age higher than the successful population. That's our interpretation of this p-value in the context of this claim.